Okay, let's go through the old exam. First question here, let's examine what we have. In the first step, we have, this is the tosyl chloride. There it is abbreviated. And we have it drawn out. Pyridine is a weak base to take care of the proton. If you recall, the tosyl, mesyl, and trifle make an OH group a better leaving group. So this is going to react. We'll eventually kick off the chlorine. I'm doing it in one step, but it's not one step. It eventually kicks off the chlorine. Remember, we kick the electrons up on the oxygen, they kick back in, and then kick the chlorine off. Pyridine pulls off the hydrogen. So we've turned the OH group into a better leaving group. Turned it from a poor leaving group into a very good leaving group. Now, step 2, we're reacting with the alkoxide. This is going to do an SN2 substitution. This will come in and attack and kick off a very good leaving group. So we've been able to, with this reaction, we've been able to convert the alcohol into an ether. Okay, our next one we have, if you recognize it, this is MBS. And if you recall, MBS only brominates allylic and benzylic positions. They will not brominate any other position. Only allylic and benzylic. So, benzylic is the position next to the benzene ring. Allylic is the position next to a double bond. Now, the tetrachloromethane, this is just the solvent. Light will break a small amount of the MBS apart. It gives us a bromine radical. The bromine radical is going to abstract a hydrogen from the benzylic position. That gives us a benzyl radical, very stable radical. Got lots of resonance into the benzene ring. This is going to react then with a bromine molecule. Now, if you recall, I'm not going to go through it here. You can look back in your notes. We make the bromine from the MBS. So the bromine radical grabbed the hydrogen, and we made HBr as a byproduct. And if you take HBr and MBS, they will react and make a bromine molecule. So that's where we get the bromine from. And you can look back at your notes and see how that worked if you're interested in that. The benzylic radical then picks up a bromine, and we have brominated the benzylic position. And there is our product. Now that's our product with one equivalent of MBS. If we had reacted with two equivalents of MBS, if there had been two equivalents, then you can put 2 on. We can put another one on there on the benzylic position because we had 2 benzylic hydrogens. Both of them can get substituted if we have enough equivalents of MBS. Only 1 equivalent of MBS, we only put 1 on. 2, we put 2 on. 3 equivalents, we still only put 2 on because there's only 2 benzylic hydrogens in this particular example. So you can substitute as many benzylic hydrogens as you have. Just depends on how many you have. We only have 2 in this particular example, so that's all you can put on. So again, MBS only brominates the benzylic and allylic positions. Look at the next one here. We have a very strong base reacting with chloroform. Let's just draw it out. Here is the chloroform. It's a T-butoxide. Happens to be your bulky hindered base, but it doesn't matter. All that matters is that it's strong. This is a strong base. We need a strong base to react here so that we can get our acidic hydrogen off. So our strong base grabs the hydrogen off of the chloroform. This gives us an anion. A chlorine will leave over time, and that gives us a carbene. It's the carbene that's going to come up here and react with our alkene. We're not going to touch the phenyl ring. Thus far, we've not covered any reactions that will react on a phenyl ring. We will in organic 2, but not here in organic 1. Now, our carbene will react with the alkene. We'll get a pair of electrons into the double bond. We take a pair out of the double bond and back to that carbon. So you make a 3-membered ring. And in this particular one, we still have the 2 chlorines on. So there's our product. Our next one here, we're reacting with thionyl chloride, SOCl2. Let's draw out the thionyl chloride. There it is, all drawn out. Let's see what else we have. We have a tertiary alcohol, and we have a primary alcohol. Now, if you recall, we talked about thionyl chloride. And that was going to substitute a chlorine on in the place of the OH, but it only reacted with primary and secondary. We also did, we could put a bromine on. If you recall, we used tribromophosphine, and we can put a bromine on in the place of the OH. So the tertiary alcohol will not react, but the primary will. So the primary attacks the sulfonyl group. If you allow me, so I don't have so much to draw out, I'm just going to draw all this as an R group. So there's our alcohol attack the sulfur. Electrons will kick back in from the oxygen, reform the double bond, kick chlorine off. That chlorine comes in and attacks the CH2 carbon here and kicks off our leaving group. Any oxygen with a full plus charge is a good leaving group. And then that gives us our chloride. So this was just SN2 here. And there's our final product. So only the primary reacted, the tertiary will not react. Phenols also do not react. You have to be able to have something that can do an SN2 right here. So tertiary alcohols will not work, phenols do not work. Our next one here, we just covered Friday here, the last day of class. MCPBA, that's metachloroperoxybenzoic acid. That's going to make an epoxide there on the where the double bond used to be. It'll react with the double bond and make an epoxide. Now this one did say show stereochemistry. So when we make the epoxide, the oxygen can add from the bottom or it can add from the top. So those would be wedges. So you just switch the dashes and wedges, which would be the enantiomer. So I showed the oxygen coming in from the bottom, but it could also equally come in from the top. Alkenes are flat, doesn't matter which side we add. Now, we've made the epoxide here with the MCPBA. Second step, we have a nucleophile that we're reacting with. That is a base. Full negative charge on the sulfur, full plus charge there on the sodium. So with the base ring opening of epoxides, we're going to open that ring. We talked about epoxides like to break apart. They're highly strained. We've got 60-degree bond angles, and those carbons want to be 109.5, so they like to break apart. So if we use a base to come in and break it apart, the base is going to go to the least substituted carbon of the epoxide ring. So you've got a choice. You've got these two carbons. Both of these two have partial positives. The oxygen is pulling electrons away from those carbons, so both of them have partial positives. You've got a choice on which one you're going to go to. And it's easier for that nucleophile to attack the least substituted carbon of the epoxide ring. Now, when this came in an attack, this is SN2. It's going to come in and do backside attack and kick the oxygen out. So that sulfur had to come in on a wedge if my oxygen is on a dash. Now the oxygen stays on the dash over here. You break this bond, but it still stays a dash here. And you still have the enantiomer. Enantiomer again is where we've got the dashes and the wedges switched. Now last step, we're adding in water. That's just a proton source. That's to get us neutral. So this will come and pick up a proton off of the water. So there's our product with the correct stereochemistry. You have a racemic mixture of the two enantiomers, but the sulfur and our OH are on opposite sides. So when that sulfur came in, it's got to come in from the backside, anti to the oxygen. They'll be on opposite sides, or whatever a nucleophile is. So this in class, I did a couple different examples. Any good nucleophile can open up that ring. Any good base can open up the ring, and we get attack at the least hindered carbon, least substituted carbon of the epoxide ring. Next one here we have osmium tetraoxide. This is going to make a diol. So that osmium tetraoxide, I want to draw it out and react it. If you know it makes a diol, you can just go ahead and write the diol. It does say show stereochemistry for this one. So we move the electrons around the cyclic array. Man, that's going to be hard to draw. Let's see what we can do. So the osmium tetraoxide comes across and adds on these two carbons. Now the hydrogen peroxide and hydroxide base there, that will break this apart. It breaks apart here and here, and we make a thin diol. When we add the osmium tetraoxide, those two oxygen have to add to the same side. Now this is, alkenes are flat, so they can add from the top or the bottom. So do we have an enantiomer? Think about it a minute, look at it. No, there's symmetry through the molecule. So you do not have an enantiomer here. If both of them were dashes, it's the exact same molecule, just flipped over. If both OHs were dashes, it's the exact same molecule. There's symmetry through there. So there is no enantiomer. So we made a thin diol. We also talked about we can also use potassium permanganate if it's cold. If you keep the potassium permanganate cold, you can also make the thin diol using cold potassium permanganate. Next one here, we are reacting with bromine. Bromine only. There's no heat, no light. This is not radicals. So you've got to pay attention. Do I have heat or light that would generate radicals, or is it just bromine by itself? So we have just the bromine. There's no heat, no light, no radicals here. Now, the bromine, let's draw it out there. As the bromine gets closer and closer to the double bond, the electrons in the double bond start to repel the electrons in the bromine molecule. So you get a buildup of partial negative on the one furthest away, partial positive on the one closest to the double bond. Eventually, enough charge builds up that the electrons out of the double bond are going to come out and grab the one with the partial positive charge. So one of those two carbons hits the bromine. One gets a plus charge. So the bromine adds that on the end. The other one gets a plus charge. Now remember, the bromine bridges across and holds that in place. We don't have any rearrangement with these. Bromine's going to hold it in place. Now we kicked off the other bromine, and that's going to add to the carbocation. And so we've added bromine across the double bond. You get one bromine going to one carbon of the double bond, one going to the other carbon of the double bond. So you'll have to be careful with the bromine. Do I have just bromine adding, or chlorine just adding, or do we have light in there or heat to make radicals? Radicals, I'm sure there's one on this old exam somewhere. And then we got one later that we'll do. Our next one here, we have hot potassium permanganate. We just talked about just a moment ago, if it's cold, we make a diol, but with the heat, we cleave the double bond. So we're going to break the double bond. You're not going to touch the phenyl ring. Phenyl ring stays like it is. They're too stable. So we don't break those double bonds. Leave the phenyl ring alone. We are going to cleave the alkene. Now, if you recall, with hot potassium permanganate, let's just go through them all. Disubstituted carbons of double bonds make ketones. Monosubstituted carbons of double bonds make carboxylic acids, and unsubstituted carbons of double bonds make carbon dioxide. If we take a look at what we have here, this one is monosubstituted, and the other one here is unsubstituted. The unsubstituted one is going to make carbon dioxide. We get CO2. So we broke that. This carbon makes the carbon dioxide. The other carbon becomes a carboxylic acid. We don't change the number of carbons. Keep track of your carbons. Okay, there are our products. To make a carbon dioxide molecule, and we make the carboxylic acid. Our next one here we have, let's examine what we have. We have diiodomethane. We have zinc and copper, zinc copper alloy. Zinc, if you recall, this is going to insert in between one of the carbon iodide bonds and makes a carbanoid. The carbanoid reacts like a carbene, but it's not a carbene. It's more stable than a carbene. So this is going to react just like a carbene. We're not going to touch the phenyl ring, but it will add to the double bond. So it reacts just like a carbene. We're going to add to that double bond, and you make a 3-membered ring, a cyclopropane ring. There's our product. We're adding the CH2 group across that double bond. So reacts just like a carbene. Okay, our next one says to show stereochemistry. First step, we are reacting with a methyl chloride. Remember, tosyl group, methyl group, triple group make an OH group a better leaving group. It turns that poor leaving group into a good leaving group. So this will attack and eventually kick off the chlorine. I'm showing it in one step, but it does not happen in one step. And really, notice on the old exam it's not written there. There should have been pyridine in there to act as a weak base to pull off the extra proton. Now we've put the methyl group on. So we've made that poor leaving group into a good leaving group. Now our second step here, we're going to do SN2 substitution. This will do backside attack, kick off the leaving group. We have inversion and configuration. So that dash will now be a wedge. And there is our product. You may also, so I did SN2, you may also get some E2. They're always competing with one another. You may also get E2, but you still will get a significant amount of SN2, and that's what we were looking for there. Okay, our next one here, we are doing the ozonolysis. We have ozone here in the first step. So ozone is going to react across the double bond, making ozonide. Dichloromethane is just a solvent. DCM. We've used that in the lab many times as a solvent. So we're reacting with the ozone. O3 is ozone. That makes an ozonide, and then the dimethyl sulfide will break the ozonide apart. Now, if you recall what I told you on these, we just simply cleave the double bond, and those two carbons, leave everything just like they are, make those carbonyls. So this is going to give two aldehydes. That's an aldehyde. You want to see there's a hydrogen right there. So let's just put the hydrogen on there. That makes it easier to see. That is an aldehyde. And the other side is also going to become an aldehyde as well. So both of those two carbons, this is monosubstituted, that one's a monosubstituted, they will give the aldehydes here. So ozonolysis is easy, just cleave the double bond, make both carbons just like they are, just make both carbons a carbonyl group. Just add a double bonded oxygen. Now you're not changing the number of carbons. Make certain you keep the same number of carbons there. Okay, let's take a look at this one. First step, we have a strong acid. Look for something to protonate. We're going to protonate the double bond, the alkene. Not going to touch phenyl. Now you got to decide which carbon is going to get the hydrogen. Which one gets the plus charge, which one gets the cation. That CH2 is going to pick up the hydrogen. We put the hydrogen out here, makes a CH3, and that gives us a secondary carbocation. If I were to put the cation here and the hydrogen there, we'd have primary. Secondary is more stable. Now that is indeed a secondary carbocation. So with carbocations, watch for rearrangement. We can do hydride shifts and methyl shifts if we can get to a tertiary. Now you must shift from a beta position. Alpha is where the cation is, next one is beta. And it's got a methyl group on it, and it's also got a hydrogen. Which one are we going to do? We're going to do the hydride shifts. Hydride shifts occur before methyl shifts. Plus if you move the methyl, you'd wind up with a secondary carbocation. Move the hydride, you get tertiary carbocation. So you got to go to something more stable, so we're going to have a hydride shift. Hydride's going to come over to where the cation is. That gives us a brand new carbocation. There's our carbocation. Now our nucleophile can add. We've got everything done here. Water is the nucleophile. We'll take more water to pull off the extra proton. And we're finally to the product after the first set of reagents. We have an alcohol. Now our second set of reagents that we're adding in We are adding in sodium hydride, I think it was, yeah. Hydride, H minus, strong base. That's going to pull off the proton off of the alcohol. That gives us an alkoxide. So that's our product after the second set of reagents. If you want to show the sodium there, you can. Balances charge out. Just spectator ion, not involved in the mechanism. And let's see, third set of reagents. We're reacting with an alkyl halide. That is a primary alkyl halide. So this is we have an alkoxide, primary alkyl halide. This is going to do SN2. This is the Williamson ether synthesis. We're going to attack, do SN2, attack and kick off the halogen. And we've made an ether. There's our ether product. I've gotten through 3 pages of the old exam. Got 2 more pages to go. And I'm going to take a break. So I'll do the others in a part 2 of the video.